We talked briefly before about this idea that a sample mean, let's say we'll call it X bar, might be a good or a bad estimate of the associated population mean mu. It really just depends on the sample that we take. We might get lucky and pull a random sample that does a good job representing the population, and therefore that sample mean is close to the population mean. Or we might get unlucky or just do a bad job and find a non-representative sample where the sample mean does not do a good job estimating that associated population parameter, the population mean. This is what we call a point estimate. So the sample mean is a point estimate for the population mean because these are single points, they're single values. In the same way that sample standard deviation is a point estimate for population standard deviation. Now, the benefit of using just a point estimate is that it's pretty easy to do, right? If this is what we're doing here, we can pull a sample, we calculate sample standard deviation, and we say, okay, based on the value we found for this standard deviation for this single sample, we estimate that population standard deviation is equivalent to that sample standard deviation that we found. It's pretty easy to do. But the drawback, of course, is that calculating just that one point estimate doesn't really tell us how good or bad that estimate really is. Again, the point estimate could be good, it could be a bad estimate. We wouldn't really know either way. So in contrast to a point estimate, which doesn't necessarily do a great job, what we instead may choose to do, is calculate an interval estimate, which gives us a range of values in which the population parameter may lie. Of course, finding an interval estimate is a little harder to do. It takes a little more work than the point estimate, but it gives us a lot more information. So if we use an interval estimate, and we touched on this very briefly in a previous lesson, but if we use an interval estimate, we're able to make statements like, I'm 95% confident that the population mean lies in the interval A to B. Now, that confidence we just mentioned, the 95% confidence, is what's called the confidence level, or we'll call it CL for short. And when it comes to confidence levels, we will very often use either 90% confidence, 95% confidence, or 99% confidence. Those are the most commonly used confidence levels. And what the confidence level really tells us is the probability that an interval estimate will actually include the population parameter. So for instance, if we choose a 95% confidence level, and using that 95% confidence level, the interval we calculate is, let's say, 11 to 15, then what we're saying is that there's a 95% chance that the population parameter, we'll say the population mean, lies somewhere between 11 and 15. Or another way to put that is that for 95% of the samples that we could take, so if we were to take 100 samples, then 95% of them would give us an interval where the population mean lies inside of that interval. 5% of the samples we take will give us an interval outside of the population mean. So let's say that the population mean is actually, we'll say, 13. What we're saying is that 95% of our samples will give us a confidence interval around 13, like this one, 11 to 15. But 5% of our samples might give us an interval like, we'll say, 14 to 18. And obviously the interval 14 to 18 does not include the population mean 13. 13 lies outside of the interval 14 to 18. Now, before we go further, you might be wondering, why wouldn't we always just choose the largest or highest confidence level? Don't we always want to be as confident as we possibly can be? The answer is yes. Of course, we want to be as confident as we can be, but choosing a higher confidence level comes with drawbacks. For example, in order to achieve this higher confidence level, we may need to take a larger sample, and taking a larger sample might not always be possible. So there are other factors we have to balance against our level of confidence. In general, yes, we want the highest confidence level we can get, but not at the expense of some other important aspect of our sampling and hypothesis testing procedure. And so we kind of have to balance those two things against each other, and we'll talk about that in more detail later on. Now, this idea of confidence level is directly related to a really important value in statistics, which is called the alpha value. We indicate it with the Greek letter alpha, and the alpha value is simply the percentage that remains outside of this confidence level. So the alpha value associated with a 90% confidence level is 10%. The alpha value associated with a 95% confidence level is 5%. And the alpha value associated with a 99% confidence level is 1%. We also call this the level of significance. So the level of significance, or, and we'll talk about this later on too, we can also call this the probability of making a type 1 error. But either way, for now, we'll just recognize that the alpha value is always equal to 1 minus the confidence level. Now, we can always visualize the alpha value as the total area under the normal distribution outside of what's called the confidence interval. Here, we're going to be talking about the confidence interval for the mean. We'll get to that confidence interval in a second. But if we look here at a normal distribution, so this is the standard normal distribution with the mean of 0 and a standard deviation of 1, we can show here, as an example, a confidence level of 90%. What that means is that 90% of the area under this distribution, or the area under the curve, is contained within these boundaries that we've set, which means, of course, that 10% of the area under the curve lies outside of these two boundaries. So if 10% is the alpha value, it's the area outside of this 90% that we've centered here in the middle, then that means that in this lower tail, we're going to have this 5% value, alpha divided by 2, and in the upper tail, we're going to have alpha divided by 2, or 5%. So we take the total 10% that lies outside of this 90%, and we divide it exactly in half to put half of the alpha value in the lower tail and half of the alpha value in the upper tail. So everything's evenly distributed here, the 90% in the middle, half the alpha value in the lower tail, half the alpha value in the upper tail. And in this case, with a 90% confidence level, that 90% goes in the middle, which means we have 5% on the left and 5% on the right. What we can say then, because this is the standard normal distribution, Z, we know that to find this boundary right here between the lower 5% and that middle 90%, we would need to look up in the body of our Z table, this 5% value here. If we locate that 5% value in the Z table, we find a Z-score of negative 1.65. To find this boundary right here, this upper boundary, we have the 5% in this lower tail and then the middle 90%, which means this boundary right here separates 95% of the area on the left from this last 5% of the area on the right. So we would look up 95% in the body of our Z table, or 0.9500. And when we find that value in the body, we see that it's associated with a Z-score of positive 1.65. Now, of course, it makes sense here that we get exactly opposite Z values because this middle 90% is perfectly centered at the mean. It's symmetric around the mean. And so the distance from the mean to this lower boundary here is the same as the distance from the mean to this upper boundary here, and so we're going to get opposite Z-scores. That being said, now is a good time to mention, remember we said that 90%, 95%, and 99% are the most commonly used confidence levels. Well, because we're always centering that percentage of the area in the middle of this standard normal distribution, that means we're going to have these little symmetric lower and upper tails on either side of that middle 90%, 95%, or 99%, which means we're always going to get opposite Z-scores. So when we choose a 90% confidence level, we will always find the Z-scores negative 1.65 and positive 1.65 that bound that middle 90% of the area. If we use a 95% confidence level, our Z-scores are positive and negative 1.96. And if we use a 99% confidence level, our Z-scores are always positive or negative 2.58. So because we very commonly use these confidence levels, that means, of course, that we will very commonly use these Z-scores. So we'll see these values, 1.65, 1.96, and 2.58, come up all the time over and over again as we start to work through the hypothesis testing process. So it's worth pointing them out here. Now, with all that background, let's talk about this main idea here, which is the confidence interval for the mean. Going back to this idea of point estimates versus interval estimates, the confidence interval is the interval estimate that we're talking about. Now, the formula that we use to find it, and we'll break this down, is this formula right here. So this is the interval from A to B. This is the left edge of the interval A, or the lower edge. This is the upper edge, or the right edge of the interval B. So we have this interval from A on the left side to B on the right side, and it's equal to, you can see here, the sample mean plus or minus the t-score that we find, multiplied by, and this value here you may recognize as standard error, which is sample standard deviation divided by the square root of the sample size. So sometimes you'll see the formula written this way, where we have standard error written out as sample standard deviation divided by square root of sample size. And sometimes you'll see the formula written this way, where we have S sub X bar, which indicates standard error. But either way, here's the first thing we want to point out. We are showing in our confidence interval formula a t-score, both here and here in both representations of the formula. But up to now, we've been talking about z-scores. We talked about the standard normal distribution here with z. We talked about these z-scores associated with each confidence level. Well, we can use a z-score if we happen to know population standard deviation. But whenever population standard deviation is unknown, which of course, as you can imagine in the real world, it is almost always unknown, then we need to use a t-score instead of a z-score. But if you did happen to know population standard deviation, then instead of using t here in these formulas, we would use z in its place. But assuming, of course, that population standard deviation is unknown, which is most likely the case, then we'll need to use a t-score, and this will be our formula for the confidence interval. Basically, the idea for using a t-score when population standard deviation is unknown is that sample standard deviation is, of course, a less reliable predictor of population standard deviation than population standard deviation itself. So because S here may not be perfectly accurate, we need to use a more conservative t-value instead of a z-value to find the confidence interval. In the same way, even if we did know population standard deviation, we would still have to use a t-score if our sample size was small, because in the same way, we would consider that small sample size to be maybe not so reliable, and so we would use a more conservative t-score instead of a z-score. So just to take a simple example here so we can show how to calculate the confidence interval, let's say that the mean exam score of a sample of 10 randomly selected students is 86.7. So we'll say that our sample size is n equals 10, that our sample mean is 86.7, and we'll say that we calculated a sample standard deviation of 5.72. And what we want to do now is find a confidence interval for the population mean at a confidence level of 99%. So we want to be really confident here in our result, and let's see what that looks like. So because population standard deviation is unknown, and even if we did know it, because our sample size is small, and by small we mean n is less than 30, our sample size is 10, we will have to use a t-score instead of a z-score. Because we know that our sample size is n equals 10, that means degrees of freedom is equal to 10 minus 1, or 9. And so if we pull up our t-table, and this is just a section of the t-table that we can use, we look for degrees of freedom of 9. We see that over here on the left-hand side. And then we want 99% confidence. So if we come down along the bottom to 99% confidence, we see 99% confidence here. We have degrees of freedom of 9. And so if we find the intersection of that row and column, we get this value here, 3.25. Now, if we substitute what we know into our confidence interval formula right here, let's say that we get the sample mean, which we know is 86.7, so 86.7, plus or minus the t-score that we found, 3.25, so 3.25, and then we multiply that by sample standard deviation, which we calculated from our sample to be 5.72, so 5.72, divided by the square root of sample size. Our sample size is n equals 10, so we get square root 10. And if we use a calculator to find this value, what we get here is 86.7 plus or minus this 3.25 times 5.72 divided by root 10 is approximately 5.88, which means then that our confidence interval is A to B equals, on the lower end of the confidence interval, we have 86.7 minus 5.88. And on the upper end of the confidence interval, we have 86.7 plus 5.88. And the result there is a confidence interval, A to B, that is equal to, on the lower end, 80.82, and on the upper end, 92.58. And that is how we calculate a confidence interval. What it says here, the conclusion that we're basically making, is that we are investigating some population of students. We took a random sample of 10 of those students, and from those 10 students, we calculated a mean exam score of 86.7. So we added up the exam score for each of those 10 students, and for those 10 students, we calculated a sample mean of 86.7. So the mean test score was 86.7, and from that sample, we calculated a sample standard deviation of 5.72. Now, if we were just using a point estimate, like we talked about at the beginning, we could stop there and say that we expect that the population mean, so for all of the students, not just these 10, but for all the students in our population, we expect that the mean exam score is about 86.7. But again, going back to the original point, this particular sample of 10 students might be a really bad estimate of the larger population. It might not be very representative. It might do a bad job estimating population mean. It might also do a really good job, but we don't really know either way. It's just a quick and dirty way to find an estimate for population mean, but it doesn't say anything about how confident we are that this is a good estimate or a bad estimate. So instead, we compute this confidence interval, and because we used a confidence level of 99%, remember we looked up this 99% confidence level in our t-table, we had to use a t-score instead of a z-score because, number one, we didn't know the population standard deviation, and even if we did know it, we were taking a small sample. We had a sample size smaller than 30, so either of those factors would have required us to use a t-score. We had both of them, so we certainly had to use a t-score instead of a z-score, but we looked up that t-score, and now this confidence interval is an interval estimate. It tells us that we are 99% certain that the population mean, the mean exam score for the entire group of students, the entire population, falls somewhere between 80.82 and 92.58. And as you can see, in a lot of ways, that gives us a lot more information than just this single point estimate where we calculated a sample mean of 86.7 off of just one sample of only 10 students. Now, remember before we talked about trade-offs with the confidence level? Here we chose a 99% confidence level, and we found an interval, let's round here. We found an interval that said that the population mean was probably between about 81 and 93, just rounding these values to the nearest whole number to make it a little easier to see. But going back to those trade-offs, what happens is if we're willing to give up some confidence, so maybe instead of choosing 99%, we're instead willing to settle for a lower level of confidence and choose 90% confidence, decreasing our confidence level will actually narrow this confidence interval. So maybe the confidence interval associated with 90%, and I haven't actually calculated it, but maybe it would be something like 85 to 90 instead of 81 to 93. In other words, the higher the confidence, the wider the confidence interval, the lower the confidence, the narrower the confidence interval. And we like a narrower confidence interval because it really hones in on or gets us closer to, gives us a smaller interval in which our population parameter, our population mean, likely lies. But we can't be quite as confident about that narrower interval. To give you another example, if you asked me to find an interval around the mean height of all American females, so the entire population is every female in America, and we're interested in the mean height of that population, I might be able to tell you that I am 99% confident that that population mean lies somewhere between 4 feet 10 inches and let's say 6 feet 3 inches tall. We can be virtually guaranteed that the population mean is somewhere in this interval. This is a really wide interval. But if I start to narrow that interval and I maybe find an interval like 5 feet 4 inches to 5 feet 6 inches, well, I really narrowed the interval, but maybe I'm only 90% confident or even less confident that the mean height of all American females is somewhere in that narrower interval. So the higher the confidence level, the wider the interval has to be. By definition, the narrower the confidence interval, the lower our confidence level. So that is how we calculate the confidence interval for the mean of a population. Next, we'll use all of the information that we've gathered about z-scores and t-scores, how to take samples and calculate confidence intervals, and we will turn toward hypothesis testing and the steps that we take to investigate a hypothesis from beginning to end.